Um, Hi, I'm Tahsin Kabir. I am a master's student at UNC Chapel Hill. I'm also a research assistant at RANSI. I'm working in the resource-aware data-centric collaboration infrastructure project. We are using iRODS. Okay, so in my talk, I'm going to brief about the RADII project a little and why are we using iRODS in RADII, and demo one of the RADII policies converted into iRODS rule and how it is executing. And I would show some experimental results done in iRODS. So RADII is a middleware to facilitate data-driven collaboration amongst different scientific research groups. There is a large gap between the procuring infrastructure and how to manage data at the same platform. So what we are trying to do in the RADII project is to provide scientists with an easy-to-use interface where scientists can create data collaboration models and the workflows and in an easy, very intuitive interface. And then in the RADII project plans to map all these data processes and computation to underlying infrastructure and provide elastic data provisioning and deprovisioning. So this is the high-level diagram of how it's going to work. So a set of researchers generates data at one research group, and another set of researchers analyze those data and create results. Another research group use those analyses to create further results and store them. And okay, so why are we using iRODS in RADII? So one of the main features that iRODS provides are the policy enforcement points, which are very easy to map to different collaboration events. And also it reduces the complexity of the RADII system itself, because we can convert the RADII policies into iRODS policies that will not have to be in the system of RADII. iRODS can manage all those provisioning and the data enforcement policies. Also, since a lot of collaboration happens in geographically distributed places, iRODS can easily be used to connect to different data stores located at different places, and it provides elasticity. Also, since we are going to employ resource awareness, iRODS provides its resource monitoring framework, so we wouldn't have to create our own resource monitoring services. And since there would be resources, those are geographically local, and iRODS provides an easy way to create composable resources based on different geolocations. And since the end user would be scientists, we wouldn't want scientists to know a lot of details about how the system is implemented and what resources are being used. the users will provide a metadata for each of the files, and based on those metadata, this system will decide where to store them and place them. So this is one example of the RADII policy, where if a file has a tag of red and the user iRODS pushes the file would be automatically stored in the site SL. If the user is Bob, then the file will be placed in the location UNC. And the file tag red can only be used, read by Adam, cannot be read by anyone else. And so these are the policies described in JSON. And I am going to, so these policies are, RADII policies are then converted into iRODS rules that, that translate these policies into iRODS language. I'm going to show an example of, so this is the iRODS iRODS vanilla rule file. It has nothing, no extra rule in it. So one of the module of RADII converts the JSON to rule files and pushes them in the iRODS resources quoted ARIFA. So what it's going to do is push the rule file based on the JSON to the iRODS resource servers. So now it has all the required rules for that policy, and if we look at the rules, so if a user RODS, user Bob pushes a file using the red tag, it automatically gets stored into the UNC store. So there were several resources. The end user would not have to provide any specific resource location. So yes, so based on the rule, if the user provides a blue tag, the file gets stored into the TAMU site. And also, we can see that the file can only, if the file is tagged as blue, it can only be retrieved by Adam. If the user if Bob tries to get the file, he cannot. Whereas if only Adam can retrieve this file. So it was very easy to convert such rules to iRODS rules, and I think it would have been far more complex to keep all these within our system and create another interface to provide user with such capabilities. So I did some sorry. So I did some experiments based on selecting the best node to get data from, or selecting the best node to store data based on the current resource utilization of those servers. iRODS provides the resource utilization lookup for the node-specific information. But in a network where there is multiple resources connected in a meshed way, where each of the end-to-end network links throughput and their current usage also matters, the end-to-end parameters also plays a significant role in the performance when we try to put a file. So based on those experiences, I created throughput, end-to-end throughput and latency and instantaneous transfer collection services that we included in case of a file put where there could be multiple candidate storages or multiple candidate storage servers to read data from. And in that case, we looked into the end-to-end throughputs for side A to B and the current uses of the CPU in the side B and other resource information. In most cases, the memory, the swap, and run queues, these monitoring information from iRODS were not that useful. So we only use CPU, current storage usage, network in and out, instantaneous transfer, latency in our utilization function for So this is the high-level diagram of how resources are set up in a geographically distributed way. These resources were in UCD, one in California, one in Florida, one in Chicago, another one was in Texas. So there was a high latency in between these storages. And what each of the edge nodes pushed 400 gigabytes of files simultaneously using multiple threads, using 3 threads, and each of the threads used parallel connection. And so each of the clients would first put a file into the edge node, and another copy would be at the side that has the best utilization value. End-to-end utilization value. And we found out that, sorry, these are hard to read. The blue one is based on the utilization value, and the green one is random server selection. We found that if we put the file based on utilization value, the initial put to the local resource was, for some reason, had a high response times compared to randomization based put, but in both cases they're putting in the same resources. But we found out that for the replication, the response time was less in case of utilization based. And also, so the combined response times for random was higher than the utilization value based one, and the read response time was also better for our utilization value based candidate site selection. Thank you.
There is time for questions. You converted from JSON to the rules, right?
Yeah.
Is it done only once, and then you scrub it, or you just keep it like that itself? Is it like, what happens if you want to change it?
I think we haven't done the alteration of JSON files yet, but my assumption is it would be fairly easy to change the prepended rules to the core.re file, the rule files.
One more question?
Yeah, you actually found a bug for us. You, with your multi-homed network layout,
Yeah.
You identified that we were resolving to IP too soon. And so we fixed it, and now we ship host names around everywhere, which is part of the mantra of host names, host names, host names. Other than that, what was your most, I guess, surprising thing when working through all this? I mean, you did a lot of work for, you know, what you've shown in one chart.
Yeah. What was the most difficult thing?
Difficult or surprising, whatever.
I think the one of the I would say drawbacks that I found out in iRODS was that it uses decentralized iCAT server, and it does make a lot of differences when I am dealing with a high latency data collaboration system. I think if iROD provided a quicker way to get system monitoring information by distributing those data, would have been fairly faster for our collaboration testbed.
So if you had a rule that picked the closest resource in terms of network latency, would that have improved the performance?
Yeah, we are planning to incorporate our latency and throughput-based monitoring information into the rule in future iterations.
Very good. Let's thank our speaker.
Thank you.